Hello everyone, welcome to another video lesson discussion in general mathematics. This time we're going to have propositions. The following are the objectives of our discussion. And these are the questions that you should be able to answer at the end of the discussion. Okay, let us define logic. Logic is the science of thinking and correct reasoning. So one of the most renowned logician is Aristotle. He was the student of Plato and the tutor of Alexander the Great. His logic was used to distinguish valid arguments from invalid arguments. So we also have what we call the propositional logic. So it is a branch of mathematical logic that studies the truth and falsity of propositions. So in logic, we concern ourselves only with those sentences or statements that are either true or false but not both. Every good sentence needs a noun or a subject, an action word or a verb, and an object or the completion of the idea of the sentence. But how is a mathematical sentence different from a grammatical sentence? So when we say mathematical sentence, it has a certain truth value, and it is called a closed sentence. And if the truth value is uncertain, we call this one as an open sentence. What is a proposition? A proposition is a declarative sentence subject for affirmation or denial. It is a statement with truth value. The truth value could be either true or false, but not both. Okay, let's have an example. Determine if each statement is a proposition. Number 1, did you buy a car? So this one is not a declarative sentence, but an interrogative sentence or a question. Number 2, Honda manufactures the world's best automobiles. So, for this one, we cannot determine the truth value of this statement. Because for others, Honda could be the best manufacturers, but for some people, they are not. So, therefore, this one is an opinion, and this is not a proposition. Number 3, I am telling a lie. So, for this one, again, we cannot determine in general the truth value of this. So only I can determine the truthfulness or the falsity of this statement. So this one is called a self-contradiction or a paradox. And for number 4, 4 plus 5 is equal to 9 times 3. This one is a mathematical sentence. The truth value of this is false. So therefore, it is a proposition. Okay, let's have an example. Determine if each statement is a proposition. Number 1, all parallelograms are quadrilateral. So generally, quadrilaterals are polygons with 4 sides, and parallelograms are examples of quadrilaterals that has 4 sides. So therefore, this one has a truth value of true. So therefore, this is a proposition. Okay, number 2, rhombuses are squares. So again, rhombus and squares are quadrilaterals. They are both parallelograms, but when we classify rhombuses, they are not a square. But a square is a rhombus, but a rhombus are not squares. So the truth value for this is false. So therefore, this is a proposition. Okay, for number 3, triangle ABC is a right triangle. So this one we cannot determine the truth value, whether it is true or false, since there is no illustration. And therefore, this is not proposition, since we cannot determine the truth value. And for number 4, draw two parallel lines that are cut by transversal. So this is a sentence, but this one is a command or a direction. So therefore, we cannot determine the truth value. So therefore, this is not a proposition. So I hope it is clear to you on how to determine whether a sentence is a proposition or not. You have to determine the truth value of that. Okay, let's have now syllogism. It is the cornerstone of the mathematical logics. It deals with hypothetical or compound propositions. So, according to Webster's dictionary, it is a deductive scheme of formal argument consisting of a major and minor premise and a conclusion. So, this is syllogism. We mentioned earlier that syllogism deals with hypothetical or compound proposition. So what is a compound proposition? It is formed by joining two or more simple propositions with connective words such as and, or, not, if then, and if and only if. So we call this one as logical connectors. While a simple proposition, it conveys only one thought with no connecting words. So if we have two simple propositions and connected by logical connectors, so we will form a compound proposition. Okay, let's move on to symbolic logic. So it enables us to solve complex problems. The symbols in logics, like those in algebra, are important aids to thinking. So when we say symbolic logics, they are usually lowercase letters which are used for labels for statements. So the most commonly or frequently used letters are P, Q, R, S, and T. So the first thing that we must be able to do is to identify and symbolizes the sentences. For example, P, it is raining. So that is the symbolic logic for that sentence. So that is P. And then we also have Q, math is easy. So this is how we do symbolic logic, which are labels for uh, statements or propositions. Now, when can we say that a compound statement or proposition is true? So depending upon on how the statements are connected, the resulting compound proposition can be a negation, a conjunction, a disjunction, a conditional statement, or any of the combination thereof. Let us study the various ways in which statements can be connected. First, we have the negation. So the negation of the statement is the denial of the statement, and it is represented by the similarity symbol, this one. Okay? It is frequently formed by inserting the word not. So the negation of a sentence changes the truth value of the original sentence. Remember that a statement and its negation have always opposite truth values. That is, if one is positive or if one is true, the other is false. Example, if we have the symbolic logic P, today is Thursday, so the negation of this statement is so you have here the symbol negation of P, today is not Thursday. So this is how you negate a statement. Usually you just insert the word not. The words all, some, and no or none are called quantifiers. So these are example of statements that contains quantifier. For example, all poets are writers. No math books have pictures. And some students do not work hard. Okay, let's have an example. Negate the following statements. Mary went swimming. So the negation will be Mary did not go swimming. So sometimes it is not correct that you only insert the word not. So if you may write it grammatically correct, much better. Okay. For number 2, 3 points are collinear. So the negation will be 3 points are non-collinear. So we have the word non-collinear in mathematics. For number 3, some medicines are effective. We can negate this one as some medicine are not effective. But for the quantifiers all, or all medicines are effective, so we have here quantity, all. So we can negate this one as no medicine is effective. And then for number 5, we have the, again, this is being quantified. No real number will satisfy x squared is equal to -1. So we can negate this one as there is a number that will satisfy x squared is equal to -1. So these are some of the examples for negation. So again, it is not correct that we only insert the word not. Okay, but most of the time we insert the word not when we are negating a statements. But you have to look whether it is also grammatically correct. Okay? Okay, these are equivalent ways of expressing a quantified statements. For the statement all P are Q, so we can negate this one as there are no P that are no Q, or some P are not Qs. For example, all teachers are trained, so the negation could be there are no teachers that are not trained, or some teachers are not trained. So for some, we have, for example, some people like ice cream, so the negation could be no people like ice cream, or at least one person like ice cream. For the quantifier some, so for example, some students do not pass the class, so not all of the students are passing the class. So this could be your negation. And for no P R Q, so for example, no car is running on the rail train, you can negate it by saying all the cars are running on the rail train. So these are the alternative ways. For the quantifiers all, some, and no. Okay, let's have conjunction. So it consists of two or more propositions connected by the word and. And we use the symbol inverted B or caret. So P caret Q represents the compound statement P and Q. Example, if the symbolic logic P, logic is easy, and you have Q, algebra is difficult, and we want to form the conjunction P and Q, so we'll have logic is easy and algebra is difficult. If we have Q and P, so this will be algebra is difficult and logic is easy. So this is how you do the conjunction with two propositions or simple propositions using the word and. So this is a conjunction. Now let's have the truth value of a conjunction. So the conjunction P and Q is only true when both individual sentences are true. Meaning, if the first statement is true and the second statement is also true, so therefore the truth value of the conjunction is also true. But if one of the sentences or if one of the statements is false, just like this one, true, false, false, true, false, false, so the truth value of the conjunction is also false. Okay, this time let's have this junction. So it is consists of two or more statements connected by the word or. So we use the symbol V. Parang V siya. Okay, so P, V, Q represents the compound statement or. So you read this one as P or Q. For example, the symbolic logic P, I will pass the math exam, and then Q, I will be promoted. If we do the disjunction, we will have P or Q, so will be P or Q, I will pass the math exam or I will be promoted. So this is how you combine, you do the disjunction using the word or. Now, what is the difference between inclusive or and exclusive or? So for inclusive or, it includes the possibility that both things may happen or both statements are true. For exclusive or, if the statement does not include the possibility that both things or both statements may happen or it is true. So for the truth table of the disjunction, so it is only false when both P and Q are false. So for example, you have here the first statement is false and the second statement is also false. So the disjunction is false. But if one of the statements is either true or false, it is still true. Okay? Okay, this time let's have conditional statement. So we have the symbol, this one. It is an arrowhead, a straight line with an arrowhead pointing to the right. So that implies the statement that can be written in an if and then form. So you read this one as if P then Q, this one, or P implies Q. Now, every if and then statement has two clauses. So the clause that follows the if word is the hypothesis. So it indicates the person or subject about which something is said. while the clause that follows then is the conclusion. It shows what is being said about the person or object on question. Now, in any particular case, if the hypothesis is true, then the conclusion is also true. Okay, a conditional statement is usually written in an if and then form. But there are conditional statements that are not written in the if and then form, but it contains indicators which helps detect the premise or the hypothesis and the conclusion. So for the premise or hypothesis indicators, we have the word if, when, because, follows, from, and since. And for the for the conclusion indicator, we have the word then, so we have if and then. We also have only if, hence, therefore, and thus. So when you see this word, the statement before that follows that will be your premise and your conclusion. Okay, let's have an example. Symbolic logic P, if I exercise regularly, then I am healthy. So you have here the word if and then. So the word follows by, or the phrase statements followed by the word if is your premise, and then you have I am healthy will be your conclusion. Another example, when you sing, it rains. So we have here the word when, so that will be your premise. It rains will be your conclusion. Now, a statement can contain hypothesis and a conclusion even if the phrase if and then is omitted or deleted. For example, all squares are rectangles. So your premise here will be all squares and your conclusion will be rectangles, are rectangles. Okay, let's have an example. Rewrite the following in an if and then form. So, one lives in Iloilo is an Ilonggo. So, you can write this one as, if Jester lives in Iloilo, then he is an Ilonggo. Number 2, no ghost has a shadow. So, you can write this one as, if Casper is a ghost, then he has no shadow. Number 3, a girl looks beautiful if she has long hair. So, we can write this one as, if a girl has long hair, then she looks beautiful, or you can write a specific name. Number 4, all whole numbers are real. So, we can give an example. If 3 is a whole number, then it is also a real number. Then next, beautiful flowers are pleasing to the eyes. So, we can have, if flowers are beautiful, then it is pleasing to the eyes. So you can identify which is the hypothesis and the conclusion. And then for the last one, healthy children seldom get sick. So if you're a healthy boy, you seldom get sick. So these are examples of rewriting a statement in an if and then form. Now, for the truth table of a conditional statements if and then, it is only false when a true hypothesis implies a false conclusion. So for the table, so here, if your first statement, which is your hypothesis, is true, and your second statement, which is your conclusion, it is false. So therefore, the truth table of the conditional statement is also false. But if your hypothesis is true, your conclusion is true, so the conditional statement is also true. If your first statement or your hypothesis are false, and your conclusion could either be true or false, your conditional statement is still true. Okay, so I hope this is clear. You just look at this table. Okay, let's have biconditional. So the symbol is a straight line with a double-headed arrow. So if the two statements are connected by the if and only if, so this is called a biconditional statement. So you may also written the proposition as this way, P, I, F, F, Q. So you read this one as P, if and only if Q. For example, your symbolic logic P, Rico is a champion, and Q, he wins the last game. When we write this one in biconditional statement, we will have Rico is a champion if and only if he wins the last game. So this is your symbol. So this will be the summary of our logical connectives or logical connectors. So we have the negation, conjunction, disjunction. We have subconditional, which is also called implication, and then you have the biconditional. So these are the symbols for those statements, and these are the meaning of those symbols. Okay, that ends our discussion for today. For your output, visit the Google Classroom and then kindly subscribe, like, comment, and share. Thank you.